is that we end up with only one product, just like with the SN2. In the SN2, we only end up with one product. Okay? And our issue now comes out of it not so much stereochemistry, but kind of it's almost regiochemistry on what type of double bond you form, be it cis or trans. Okay? When is this going to become relevant? Well, if your product with the alkene exhibits cis-trans isomerism, remember when we talked about cis-trans, identifying all of those way back? You draw out your product and it looks like it has cis-trans options. You need to look at the mechanism very, very carefully to make sure you know that you're getting the proper product. Because if you provide the cis product, but the trans product is the answer, you're going to get it wrong. Okay? So, if we take a look at these two reactions, what we ended with on Monday was evaluating our difference between them. Okay? Well, we could go through and say our products were different. We had the trans, my pen works, the trans product up top, and we had our cis product down below. Okay? So that is a big difference in looking at the products. But that's a bit late to find out what product we were supposed to have. So if I tell you you have the trans product, you can draw that. But if I don't give you the product, you have to be able to look at the reactants and say, it's going to be the trans. Okay? So what we've got to do is go back to our starting materials and evaluate how the reaction works. Okay? Well, in that first reaction, we added arrows. Because it's an E2 mechanism, we're going to break the leaving group at the exact same time we pull off the hydrogen. So our strong base comes in, removes the hydrogen, which forms the pi bond, which kicks out the leaving group. All of that happens in one fell swoop. Okay? So to go through and do this, we have to have the proper alignment. The hydrogen and the bromine must be opposite each other. Okay? That's because what we're trying to form is p orbitals, or a pi bond in between. Well, for there to be a pi bond, we have to have overlapping p orbitals, which means our orbitals need to be in that proper alignment to go through and do the elimination. How do we know the hydrogen and the bromine are in the proper arrangement as they are drawn? Everything's in the same plane. Okay, we're going to be a little bit careful with parallel because I could potentially show a wedge somewhere else that makes it look parallel, and that didn't quite work. Okay, so they are in the same plane, and we notice that by noticing that they're all just a single solid line. No wedges, no dashes on that. Okay, so that lets us know that they're all definitely in the same plane. The other thing that's important, okay, is what? Do we see the alignment in this fashion with the hydrogen and the bromine still in the same plane, but now they're both on the same side of our forming pi bond? No. Okay. In both the top example and the bottom example, the hydrogen and the bromine are on opposite sides of that center sigma bond, or our forming pi bond. Okay. So as was already mentioned, or someone at least mentioned, we have kind of an anti-alignment of the hydrogen and the bromine. So if we turn and look at this as a Newman projection, the hydrogen is aimed straight up, the bromine is aimed straight down, directly behind. Okay, so they're in an anti-configuration from a Newman projection. Okay, the other thing that's important that kind of comes into this, or in this phrasing, is we bring in this planar aspect to it. Okay, you get anti and planar for that alignment. Because that doesn't sound quite good enough, and it's a little too particular because there are circumstances where we can do the elimination where it's not perfectly planar, but it's close to it. We have to have the anti-periplanar alignment, okay, of your hydrogen that's being removed and the leaving group. Okay, so you may see that reference come out of it. All we're talking about is the arrangement of the leaving group, our bromine, relative to the hydrogen that's being removed. Okay. If we go through and form that bond, everything's happening at the exact same instant, which means what happens about that forming pi bond? Can I rotate about that position? No. Okay, we are locked in that position because that's the only way the pi bond can form, which means the relative arrangement of the substituents about those two carbons are now also locked in that position when we form the pi bond. which means when I go through and look at my product, what was wedged will be on the same side as what was wedged on the other side of our pi bond. So there's our CH3, there's our phenyl. What was dashed will be on the same side as what was dashed in our starting material. What was the other dashed bond in our starting material? There's an implied hydrogen here. Okay. Why do we not show those wedges and dashes in the product? What's that? Not quite. What was that? That carbon is sp2 hybridized, which means we have trigonal planar geometry. How many of you like drawing wedges and dashes? Oh, nobody. Which means anytime you get the opportunity to not draw wedges and dashes, what are you going to do? Not draw wedges and dashes. We've got that exact situation happening here. There is no reason for us to draw wedges and dashes in this because it is a planar molecule. So we ignore the wedges and dashes, or we don't include wedges and dashes. Okay? Could we still possibly draw this structure with wedges and dashes? Absolutely. If I try to draw this structure now, there's the plane of the iPad. But could I just as easily have drawn it like this? Yeah, and if I do that, the front of this is now wedged coming at you. We could go through and show it with wedges and dashes. Okay? But it's less obvious for us to see. Okay? The iPad goes into a thin little line as opposed to a nice little rectangle. Okay? So what we're trying to do is visualize as much of the structure as possible when we go through and do our drawings. Okay? What happens in the bottom structure? So what changed? I'll erase everything and add arrows to our bottom. What changed about our starting material in that bottom reaction from the top reaction? What's that?
It's dashed as opposed to...
What's dashed? One of our phenols has now gone from being wedged to dashed. The other phenyl we did not touch. We left that one alone. Okay. What does that change about the chemistry? Well, let's look at the result. Our base still comes in, pulls the hydrogen off, forms the double bond, still kicks out the leaving group. We're still in that anti-periplanar alignment, right? Because our hydrogen and our bromine are both in the same plane. Okay? And on opposite sides. But what happens with our product? The bonds that were dashed are now on the same side of the forming pi bond. The bonds that were wedged are on the same side of my forming pi bond. What does that change about our result? Okay, well, again, because we can't do rotation about that forming bond, because everything is happening at once, we end up forming either the cis or the trans product. Okay? We are forced to form those products. There is no other option. Okay? Questions?
So for it to form cis or trans, it depends on the starting material?
In an E2 elimination, on deciding if we have the cis or the trans product, it depends on the starting material. Okay. What it's depending on is the transition state, okay? The exact alignment of your hydrogen and your bromine. That alignment must be in the anti-periplanar condition to do the elimination. Okay? Should we take a look at another example that I'm going to try and come up with off the top of my head?
Quick question.
Okay, we got a couple quick questions. Do you need to see the top one? Can I erase that still while you're asking questions? I'm going to accept that, yes.
So how did we know that it was facing that way? Like, could it be flipped?
Sorry, let me see where you're handing, where your hands are moving. What do you mean facing that way?
Like the wings, how the wings are up? Could they have been flipped and on the bottom instead?
The only thing coming out of this is that we have the cis product. And that cis product means that the phenyl rings are on the same side of the pi bond. Do I have to show those phenyl rings being up? Could I have shown them being both down?
Yes.
Yeah. All that's happening is you're looking at me now versus me looking at me where I'm standing on my head, which I can't do, so we're not going to do that. Okay? I'm still the same person, it's still the same molecule, you're just looking at me from a different angle. So you would draw me slightly differently, but it's still the same compound. There were a couple other questions.
So the bottom one wouldn't happen.
That is not what we said at all. The bottom one absolutely happens. Okay? If we wanted to look at the rate of the bottom reaction versus the top reaction, okay, what might we say about the rate?
It's gonna be a lot slower.
It should be slower because our product is more unstable. Okay, so we would expect a slower reaction because that product is more unstable than our first one because it's a cis product versus a trans. The bottom one still absolutely happens. Okay? We may have to wait longer for it to form. We may have to provide more heat to help get over activation barriers, but it will always form. Other questions while I'm trying to draw stuff?
Not related.
Was it in both cases that, like, everything that is wedged is on the same side?
Yes.
Okay.
Everything that is wedged will end up on the same side of the double bond. Everything that is cis will end up, or sorry, dashed will end up on the same side of the double bond. If you have one thing that's wedged and one thing that is dashed, where are they going to be? Opposite sides of the new double bond.
So the bottom one, would you have less, a lower percentage of that one because your starting position for the lower one is in a, or is that in a higher energy state, so you wouldn't have as many that are in that conformation? Because you have the
So,
cells basically on the same.
There's a couple things that we want to address there. Number one, we would expect for this bottom reaction, in comparison to the first one that's now erased, okay, we would expect a slower rate.
Right.
Because what we have is an arrangement of those phenyl groups that is sterically hindered. That is not a favorable state to be in. That's going to slow this reaction down. The next thing I want to address is that you said conformer of this structure. Okay. The two starting materials that were drawn up here, and I'm now getting kind of upset because I need to show it. So much for drawing it all out. Compare the two starting materials up here. What is the relationship between those structures? Say it louder, you got it.
It's the stereochemistry.
It's something about the stereochemistry. Go further.
They're
They're diastereomers. Is this a conformational change? No. Conformational change is talking about the rotation of a sigma bond. These two structures are different. At no point will they ever superimpose. This is not a conformational change. Okay. If we are in a position where both options are available to us, okay, for that to happen, I'd have to have two hydrogens there. Okay. Then what would we expect to happen? Which product would form? So let me make that quick change. Quick. My eraser is really big. Everybody see what we did there as a quick change? I have to make that wedged. Yes, that'll do it. Okay. Now the relationship between these two structures is identical. Now it's a conformational change. What happens when we look at our products? Well, if we look at that first possible conformation, what we'll end up with for our elimination, shoot. Sorry, my pen is being annoying, and I drew these not in different conformational arrangements. Oh, I don't think I can draw this that fast. Okay, here. We're going to just do a whole new problem. There's our bromine. There's our hydrogen. There's a phenyl. There's a phenyl. Okay. Still going through the same idea with our elimination. Bromine, phenyl. Whoop, yep, no, I need that. What is the relationship between these two structures? They're identical. What's the difference? All I did was rotate about that bond, okay, about our sigma bond. So I took that hydrogen that was straight up and I rotated it out towards you. To do that, what happens to the phenyl? It goes away, and I bring the other hydrogen up into the plane. So that hydrogen, ooh, there's a sneeze coming on, is that hydrogen. What are the results? What kind of product would we get for the first one? Cis. What is wedged? Whoops. Oh, that'll work. Wedged. Our dashes are hydrogens. Whoa. Ran out of space there really fast. I could have just as easily have drawn that, now super small, without the wedges and dashes. I don't need to show the hydrogens because I can imply hydrogens. So those two structures are equivalent to each other. What happens in the bottom circumstance? Okay. Now the result that I would end up getting, I'm sure I can kind of match this, is we got the phenyl wedged and we have our phenyl dashed. The result of that is that I have the trans double bond. Both of these products are possible in the E2 mechanism, okay, with this particular structure. So all I'm doing is mixing identical things. Which product do I expect to get at the end of this reaction? Trans. Why do I get the trans? The trans is lower in energy. So given the choice between them, I'm always going to favor the trans. When we look at conformational analysis, which is what you were asking about, we're always going to get the trans. When we look at the questions on what's drawn up here because it's disappearing here in a second, I'm not going to draw it again. When we, don't do that button. What button do I want? That button? There it is. When we look at this system that we just talked about, what is the relationship between those two structures? They're stereoisomers. They are not conformational isomers. Okay? We only end up with one product for each of these reactions. These are now separate reactions. Okay? Two separate, entirely different test tubes running these reactions. And under those circumstances, I will only get the trans in the top system, and I will only get the cis in the bottom system. If we wanted to compare those rates to each other, we can then do that as a separate comparison. And we would predict the top one would happen faster because the trans is a more stable product. So that reaction should happen faster. Okay. But under the bottom circumstance with that molecule, we will always, always, always get the cis. Okay. Can I erase that top one again? I'm just going to accept that. What happens if we had this system drawn for us now? I'm just going to do pH for phenyl instead of drawing out those benzene rings. There is an implied hydrogen. Remember, we never imply charge. There is an implied hydrogen as a wedge there. What product do we get? Why?
Because there would be steric hindrance when you try and take the
I will agree with that if you keep going. What do you mean steric hindrance?
The larger bromine and the OH want to go near each other.
This negatively charged base is going to come in and try and get near that hydrogen at the same time as the leaving group is attempting to leave. What happens? Electron-electron repulsion. Under this conformation, we get no product. Remember, this is just a conformation. That structure can twist. Okay? What happens if it twists? The H goes up, causing the methyl to be down and wedged, and the phenyl becomes dashed and away, looking an awful lot like the bottom reaction. That's because it is the bottom reaction. What product do we expect under those top conditions? We get the cis product. Because remember, in a reaction, sigma bonds freely rotate in spin. Just because we draw a structure in a particular conformation that the reaction is not allowed, as long as that structure can rotate its bonds, I can lock into the position where I need to be. Now the chemistry occurs. You are expected to do that.
That would spin before the actual reaction.
Before the reaction takes place. Okay? Tricky? Absolutely. Yes?
Okay. I guess I just need an additional explanation.
No.
Here I just didn't understand. So it just goes through a rotation and you said something about steric hindrance.
So in the conformation we have, that elimination cannot occur.
Okay.
As drawn, that reaction is impossible. So what ends up happening is the molecule will rotate about that sigma bond. Because I can rotate that sigma bond freely. Rotates that sigma bond until I look like that bottom orientation. Now that I'm in that bottom orientation, when the OH minus comes in, where's the leaving group going? Out the bottom. So our base comes in from the top, and our leaving group comes out from the bottom. Do we have any steric hindrance then? No, because they're on opposite sides. Okay?
Okay, so we rotated something more like the hydrogen and the bromine on the same plane. And then
The hydrogen and the bromine need to be in the same plane, and not just in the same plane, but they need to be anti to each other. They have to be opposite.
I have a question.
Yes.
So, would there be a situation where it wouldn't rotate up and it would rotate down and around? Oh, it rotates up because they have to be opposite. I see. Right.
Sort of. What's my name? What's my name now? How about now? So it doesn't matter which way it rotates. There could be a way that it's prevented to rotate one direction as long as it can freely rotate through the full 360, one direction or the other. It doesn't matter because you'll end up with that same possible conformation. Okay? Okay, everybody seems to love Newman projection, so we can take it to the Newman projection and see what's going on with this. If we take that structure, okay, and we go through and do our elimination, okay, again, our strong base is coming in, attacking the hydrogen, forming the pi bond, and kicking out the leaving group. And we're in that anti-alignment. If we now took this structure and changed it into a Newman projection so that we could visualize it. So your textbook has drawn 3 nice Newman projections for you. All right, so let's draw in some colors because it's always fun. Red carbon, blue carbon. Where's the red carbon in your Newman projections? Center doesn't work for me. What was that other statement over here? It's the front carbon. In all of those Newman projections, it's the front carbon. How do you know that?
because the bromine isn't shown in the
The bromine is attached to the red carbon, so it's the one in front. Where's our blue carbon? It's then going to be the one in back. Okay? So if we look at the alignment as it's directly drawn, we just take the structure and we rotate it into our Newman projection. Notice where the bromine is. Directly down. Where's the hydrogen? Directly up. We are in the anti-alignment, elimination can occur. If we rotate the back carbon, so we're taking that blue carbon, did a horrible job with this color coordination, and we're rotating following that arrow. What happens? Well, first we'd go through the eclipsed conformation. That's a high energy transition state, so that doesn't form. It continues to rotate until we fall into another transition state where our hydrogen is now what with respect to the bromine? Gauche. What happens as our base tries to come in and react with it? That base molecule now comes in and butts into the bromine. So the base gets chased away by our leaving group. We never run the reaction. As we continue to rotate, what ends up happening? We'll get the same conformation, but on the other side, still preventing the elimination. Okay. There is one conformation that we don't have drawn up here. What is that conformation? Okay, and as a hint, it's kind of relative to this. Remember we said one of the things we needed was the hydrogen and the bromine needed to be where? Opposite was one qualifier. What's the other qualifier? Planar. There's another drawing where they're in the plane. Where's that drawing? What would that look like? Eclipsed. Why do we not evaluate the eclipsed? Because it's really high in energy, that molecule can't exist. It's at a peak. It's at a transition from going from one state to the other. Okay? So that's one reason why we don't look at that as our possible transition for an elimination. What's the other reason? What happens as our nucleophile... Oh, connect. Come on. Don't freak out on me. What happens if our nucleophile tried to come in and attack that hydrogen? It's now even closer to that bromine leaving group, preventing it from coming out. Okay? So when we talked about Newman projections, conformational analysis, and looked at all those bond rotations, you were supposed to do that a whole bunch. Okay? Why? Because that's what sets you up to understand why the elimination reaction works the way it does, or why the E2 works the way it does. Okay? Questions on that? Guess what the next question is going to be? Why do we not care for the E1? The leaving group has left. Our leaving group was on our red carbon, which means if we look at our Newman projection, our hydrogen, as long as it's in the plane of our p orbital, can be eliminated very, very easily. Or I could have rotated it where my hydrogen was straight down. Was it pH? Yeah. Get the idea? So for the E2, it's critical because our leaving group and our hydrogen kind of affect each other. For the E1, we don't care because the leaving group's not present. It's already forced itself into that kind of sp2 alignment where we're already set up. We're halfway to making our pi bond. Okay. You will notice that to do this elimination, what still has to happen? Our hydrogen still has to be in the same plane as our forming pi bond. Okay. But there will be two ways that it can align, giving us two possible products. Okay? Questions? Okay. Kind of a subtle point here. When we go through and do the elimination, you'll notice that we end up with Z and E as possible products if we have two hydrogens that we can eliminate from. The relationship between those two products then becomes diastereomers. We already addressed this. Which product we expect to be our major? The trans. Right? Does the cis still form? Yes. What's going to determine whether the cis forms in higher ratios? Right? So as a hint, I would probably argue for this particular reaction, we might be looking at 60% and 40%. What happens if instead of those being methyl groups, those are now phenyl groups? We would expect a larger ratio of our major product to our minor. Why? There's more steric hindrance. So as we change the structure, steric hindrance can increase in its importance when we go through and evaluate our products. Okay? Questions? Okay. So, Chapter 8, our big summary out of Chapter 8 is given that a reaction is E1, SN1, E2, SN2. Then, what happens with your product? Okay? That's what you're trying to do in Chapter 8. Okay? You are told to do a particular reaction, just do it. Okay? Add whatever arrows you need to. The arrow aspect is ultimately Chapter 7. Okay? How do you move from a reactant to a product? Okay, so you're doing, to a certain extent, some prediction about your products, but that prediction is on the assumption that we tell you what is happening. Right? What happens as we move further through chemistry? We won't tell you, because theoretically you now have a vast understanding of all the basics that there's no need for us to tell you, because you're already thinking about that, saying, oh, that can't happen that way. Right? So Chapter 9 is now looking at the details of your substitution and your elimination and looking at everything that's changing, the things that control each of those mechanisms, and saying, okay, that means this is going to be more important for this mechanism, and it's incredibly irrelevant for this mechanism. And all of that comes back to really having a fundamental understanding of the mechanisms involved with this. Okay? The tail end of Chapter 8 brings in a couple extra kind of topics that we'll kind of look at. When we're drawing out a mechanism, you might see acid-base reactions pop in there. Okay? What's happening with the acid-base reaction is ultimately what we talked about earlier, kind of the leveling effect. If I'm in a strongly basic environment, at no point during my mechanism should I show a strong acid. Because what happens? They neutralize immediately. So what we've got to do is evaluate the conditions of our reaction. Are we strongly basic? Then I better make sure in the course of this mechanism I do not show a strong acid. Am I strongly acidic? Well, if I'm strongly acidic, when I draw out my mechanism, I had better not show a strong base. So what things would we be looking for? In a strongly basic reaction, we can't form acids. So one of the big tip-offs that you did something wrong in a strongly basic environment, positive charge. Okay. It's not a guarantee, but it's something to be aware of. If you're in a strongly basic environment, positive charge is typically a bad thing to see. Why? What charge is a strong base? Negatively charged. What happens when a negative gets near a positive? They immediately neutralize and cancel out. So if you draw out a mechanism in a strongly basic environment and you see a positive charge, your mechanism's probably wrong. Okay. What should you be looking for in a strongly acidic environment as being bad? Negative charge. Anytime you see a negative charge under strongly acidic conditions, that becomes problematic because a strong negative is a symbol for a strong base. Under strongly acidic environment, we have lots of H plus floating around, which means the charge we want to see in our mechanisms will be positives. Okay, so we could look at it this way. These are bad things for each of those conditions. Okay. So this is yet another layer to add on top of what you do when you draw out a mechanism. Okay? It's not just draw the arrows to make it look like the product. It's now draw the arrows and evaluate each of your arrows. Does that make something that is able to form? Evaluate the acid-base chemistry from chapter 6. Okay? Intramolecular reactions. You should typically avoid these unless you are forced to do them. Okay? The intramolecular reactions tend to be very tricky, and they also tend to be fairly rare as well. Okay? So they're kind of an ultimate test of how well you understand what you're doing, which is usually a good signifier for showing up on an exam. Okay? So kind of be aware of that. Okay? Why might an intramolecular reaction be kind of rare? What does intramolecular mean? Within the molecule. So we're saying one part of the molecule attacks another part of the molecule. Why is that not going to be particularly likely?
Maybe there's something else there.
Can my hand attack my elbow? Okay. Doesn't quite work. What could my hand potentially attack? Could attack, thank you, my other elbow. Why could it attack my other elbow? There's a long enough distance between those 2 points where it can snap back and do that reaction. Okay. What's that optimal distance? What shape am I forming as my hand comes back and attacks my elbow?
A ring.
A ring. When is a ring going to be most likely to form? 6-membered rings, because they're more stable. There's chapter 4 or 3 or whatever chapter our cyclohexanes were in. Okay. If you end up forming a ring structure in that attack that's a 3 or 4-membered ring, that's really, really unlikely, because all of those bond angles are very sharp. To be able to get my hand to come back and attack my elbow, that's going to be really painful. Okay. The structure does not want to do that. Okay. Carbocation intermediates. Okay. Based on the practice that you guys have been doing, I have a feeling you guys are already sort of at least fairly comfortable with watching out for these. As soon as you see a carbocation, you should immediately be thinking, oh crap, rearrangement. Every single time, without a doubt. Whether it does it is a separate issue. Okay? But as soon as you see that carbocation, you should think, can I do a rearrangement? Okay? If it is possible to do the rearrangement, you need to do it. Okay? What do we mean by is it possible? You're taking the carbocation from a high energy state to a low energy state, which means if you see a secondary carbocation, what do you need to look for? A tertiary. Is there a place that you can shift it to quickly and easily as a tertiary carbocation? What else could you potentially shift it to? This one's trickier. I think I heard it. Allylic. Why allylic? More stable because of resonance. Okay, so you're still addressing all of those same kind of principles. You're just looking at them in slightly different situations. Okay, so acid-base mechanistic extras. So these are our bad possible options for a mechanism. Why is that first option a bad option? What am I showing is happening? So if we try to add arrows through to this, right? Oxygen has electrons, attacks the positive carbon. That takes me to my product. Okay. And then I can have the OH minus pick up the H. There you go. Hey, there's my product. Mechanism's all fine and dandy. All the arrows are perfectly valid. There is nothing wrong with the arrows. The issue is that that first step will be incredibly slow. Why?
You're going from not charged to charged. You won't want to do that.
It's not even just not charged to charged. I'm in a strongly basic environment. That means that the structure that I drew as my intermediate cannot exist. Okay, so my arrows are valid, but my structure is wrong because I'm in an environment where that's not allowed to draw. That is a very acidic hydrogen. So how can I adjust my mechanism? What would I go through and change on this? Where I would address this is what we should change is focus not on, oh, I just need to do a substitution, but focus on the chemistry of the molecule. and in this case, molecules. When we look at a reaction, we try and predict what's happening in it. What do we need to find? What was that? That's looking at the product. We don't even have a product yet. Okay. What I'm asking you to do is, if we're looking at just this, what should you be trying to do? What should you look for? How about now? What are you looking for?
You could take the hydrogen away from that.
You're still giving me a mechanistic step. I don't want a mechanistic step yet. It's simpler than that. Closer. I'm looking for the absolutely most reactive thing here. Why? What are reactions trying to do? Neutralize the most reactive thing. So what should my very first step be? Find the most reactive thing and fix it. Once it's fixed, I can then evaluate what happens in the next step. And what am I going to do then? Find the most reactive thing there and fix it, and fix it, and fix it, and fix it until I can't fix anymore. Okay? So when we look at this, what you should be seeing is not an alcohol in that alkyl halide, but what you should be seeing is that I have a metal and a nonmetal, which means I have an ionic bond. And that ionic bond is going to give me OH minus. And I know it's not PC, but what I could do with this is I like to think about it as a face test. Right? Which of those things do I know I do not want splashed in my face? Sodium hydroxide, strong base. Potassium hydroxide is an even stronger base. I really don't want that splashed in my face. I don't know what the other chemicals are, but I know sodium potassium, that one will hurt a lot. That's the one I want to focus on. What makes that molecule reactive? What charge? What do I need to find? A positive charge. So now what I do is go into the rest of the solution and I find the most positive thing I can find. What do we find? Why hydrogen?
Because it's electronegative.
What charge is that carbon? Why'd you pick the hydrogen and not the carbon? It's a dance. It's a question that we can kind of dance around and you keep seeing throughout the semester, trying to decide on what happens within this. Okay. The oxygen is more electronegative than the hydrogen than carbon is relative to the iodine. So the charge on the hydrogen is more positive than the charge on the carbon. What's the other thing to evaluate? Size. What's near the hydrogen? One atom. What's near the carbon? 4 atoms. Which is easier to get access to? The hydrogen. Given a choice between acid-base chemistry and any other chemistry, which should you do first?
Acid-base.
Acid-base, because it's easier. It's more accessible. It's more readily available. It's the faster chemistry. So we show our electrons from the oxygen come up and pick up that hydrogen. But now that hydrogen has how many bonds? Too many bonds. So what do? We break the bond by putting the electrons onto the oxygen. What's our result? That structure. Yeah, okay, yeah. That structure, you mean? H2O and our iodine. There's my product of that reaction. Ooh, that's ugly. I started with a negative oxygen, I end with a negative oxygen. Right? But I did kind of neutralize my most positive thing. So now the question is, I still have that negative. What do I need to do? Find a positive. Where's a positive for it? Carbon's one option. What's the other option? Nope, potassium won't stabilize it. The hydrogen from our water molecule. It's an equilibrium reaction. Snap. That doesn't take us anywhere. Carbon has too many bonds. We can now kick it out. Now, under these circumstances, I have a strong base in a strong base environment. that is okay. That mechanism is valid. Bottom one. What happened there? Let's try and add arrows to it to make sure we can explain what occurred. Kind of trickier. So it's a big hint. Where's that oxygen in your starting material, our red oxygen? As a hint, it's either in structure A or structure B. We said it was in A. Where did that come from? It's actually in B. So what happened? And what happens? Well, our oxygen picks up a positive charge. I don't have any problems with that. Positive in an acidic environment. That's absolutely valid.
You have the OH minus.
What did I kick out? A negative, a strong base. Can I have that species be kicked out? No. So what has to happen before I can do that? I have to attach something to it to make it not negative. Okay, so again, instead of focusing on the reaction, focus on the most dangerous thing there. Most dangerous thing there would be sulfuric acid. What makes sulfuric acid reactive? H+. So what do I need to find? What charge is the oxygen now? Positive. Does it want to be positive? So what happens? It could potentially leave on its own. This brings in a mechanistic step that I actually am going to dodge for the moment. But we could have that then come in and attack. We'd end up with our product here, except instead of being OH minus, we would have water. Do I have a strong base anymore? No. Now my mechanism is valid. I can continue to propagate this out the rest of the way. What has to happen in that next step? I want you to be very careful on this. Yes, hydrogen is the problem. What happens to the hydrogen? Picked up by water, I'll accept that. Anybody else got another way to say it?
Protonating water.
Stop answering because all of your answers are okay. Anybody else? And don't say protonating water now. Okay, fine. Don't say it. Biggest issue I want you to realize here is hydrogen is not leaving. Why? If hydrogen leaves, that word leaves means it's taking electrons. Hydrogen is not taking the electrons. Hydrogen is being removed from the structure. Okay? Which protonating water? Yes. Okay. All of those were valid explanations. Questions? So, now when you go through the mechanism, it's not just a question of, okay, now I just draw my arrows in. It's now, did that step actually make sense under the conditions that I'm in? Okay. Eventually, you will internalize this, I promise. Intramolecular, bad versus good. Under that first reaction, SN2, okay, the nitrogen attacks our carbon, causes a ring opening, which is valid. I have a negatively charged oxygen and a positively charged nitrogen. To get to the very end, I need to have that oxygen to be neutral by picking up what? A hydrogen. What do I need the nitrogen to do? It needs to get rid of a hydrogen. Okay. So how could we do that? Well, one option is we look at it as an intramolecular reaction. The negative attacks the positive hydrogen. Nitrogen picks up those electrons. Seems legit. Why not? We have a 1, 2, 3, 4, 5 membered transition state ring in that. A 5-membered ring, while not horrible, is not particularly ideal and not particularly likely. So what is likely happening? The solvent is mediating the electron or the hydrogen transfer. Okay. So that can remove one hydrogen, and we'd have our NH2. We'd still have our O minus, but we'd end up forming NH4 plus. And we end up doing in 2 steps what we had originally drawn in 1. Why would we do that? Because it makes more physical sense to draw it in 2 steps, because very likely those things are not happening at the exact same instant. They're happening in 2 steps. So what we're trying to do with our mechanism is replicate the most likely thing to occur. If I jammed that all in at once, I would have had 3 molecules involved in that. So instead of breaking it into 2, if we tried to do it all at once, what would have happened? Have an NH3 floating around. Right? If we show that, how many molecules are now in it? 1, 2, 3. What type of reaction do we have? It's the molecularity. Termolecular. How often do we get 3 people all agreeing to one overall concept? Okay. Very, very rare. The rarity is so low that we try to avoid that when we draw our mechanisms. We try and stick with just 2 molecules. Okay. So the intramolecular is a bad option, and the termolecular is also a bad option. That's why we have to split it into multiple steps. Okay. Last one, probably one of my favorite all-time kind of reactions. Whoops. Yep. What happened in that last case? Bromine absolutely has to leave, but if bromine leaves, something has to replace it. What replaces it? The oxygen. What oxygen? The one that's already attached on the ring. Okay, what type of reaction did we do? Intramolecular, which we just said was bad. How do we know this happens? Because I told you it happened. That's why it happens. Okay? You are forced to do this. How do we know in general that this reaction would even potentially occur? We went into the lab, we tested it, and that's what happened. We saw the result. Now we have direct physical evidence to support that that intramolecular reaction occurred. We have no evidence to support other intramolecular reactions occur. Until we have that evidence, we cannot say it happens. Okay, I know, that's obnoxious, but that's the way it works. Questions? Okay, we'll go through and do the exact arrow pushing. First thing that happens is we need a strong nucleophile, so we're going to do an acid-base reaction. With now a strong nucleophile, that oxygen can come in and attack that carbon, kicking out the bromine. Okay. What we have is a planar structure. If we envision the iPad, there's the oxygen coming off of that corner. There's the bromine coming off the bottom corner. Okay. It's going to do a backside attack. The oxygen comes over, shares its electrons with the backside of that carbon-bromine bond. What happens? Forces the bromine to leave, and I now have the oxygen connected to 2 carbons. There's my ring structure. It's known as an epoxide formation. Yes, they happen, and we'll look at a couple other mechanisms for it, potentially later in the semester, but not later today. I just wanted to make sure you saw an example of intramolecular working. Okay. Carbocations. If we're running an SN1 reaction, okay, so if we tell you this is SN1, what's the first thing that happens? Iodide leaves, and we end up with? Be more specific. We have a secondary carbocation. Bottom of the rung as far as stability of carbocations. Why is it the bottom of the rung? Don't we have primary and zeroary? Why no? They can't form. So as far as stabilities of carbocations go, the secondary carbocation is the absolute worst carbocation we can have because the other ones can't physically form. So secondary carbocation, what do we want to do? We want to see if we can make it tertiary. So what we're going to do is look around that and look for a position that's tertiary. We'll notice that we do have a tertiary carbon up top and a primary carbon down below. Where do we want the carbocation to go? The tertiary. So we can say, okay, it just does it, and we hope that we weren't asked to do a mechanism. Awesome, you're asked to do a mechanism. What happens? We do a hydride shift, and officially my arrow is even off, because where are the electrons? In the bond going to the atom. The hydrogen has no electrons. The electrons are in the bond. Okay, and we've done our hydride shift. Now our iodide can come, or sorry, our water can come in, and we can do our substitution. Let's push it a step further. New problem. What happens now?
You can't do a hydride shift.
Good answer. Why? What we are looking at is the immediate positions around the carbocation. One is primary and one is secondary. I started as secondary. Is there any reason for me to go to another secondary that's not any more stable? No, which means no rearrangement occurs. This is the carbocation and it continues through the rest of the reaction. Okay? So what we're looking at for our rearrangements is the immediate positions next door, not further down the line. Yes, I have a tertiary carbon here. That is too far away to do the hydride shift. Why? Because you're transferring electrons through space. Electrons are unstable. Okay? Questions? Okay, we are on slide 8 of 37, sweetness. So I will preface this with, I have to get through this information in chapter 9. So it either happens really quickly today, or it happens today and a video gets posted online, and then Monday is straight up review, or it happens today and Monday. What's your preference?
The first option.
First option, I agree. I like that option too. So Monday will be primarily a review. So anytime or anything you've got questions on, that is a good time to flag them and bring them in on Monday so that we'll go directly into questions. So chapter 9 is now looking at substitution and elimination reactions and looking at all of the features that contribute to them. If you think back to when we looked at our substitution and elimination reactions, you should have noticed that I had this kind of format popping up all the way through it. You had some colors showing there. We had a blue, which doesn't show up very well, but it's there. I promise you that is blue. Okay? That's in reference to our substrate. Okay? The leaving group is in purple. Also important in our substitution and our elimination reaction. The next thing that we see show up as a color code is the nucleophile. Officially, it's nucleophile or base. If it's a nucleophile, we have substitution. If it's a base, we have elimination. Okay? What's the difference between a nucleophile and a base? Ooh, that's a really hard question, because both of them are negatively charged. That's why we talk about it in this chapter. Okay. So it's in reference to what they do, but if you're just giving a negatively charged species, how do you know what it does? You have to have some other kind of reference on that. The last piece of information that's important to kind of factor into your decision is your solvent. Okay, so in our solvent, we've got two possible types as far as we're concerned, protic and polar aprotic. So what we're going to do is look at each of these four things, come up with ways to describe them so that we can then think about how they would affect each of our mechanisms. Okay? So that's our primary goal with this chapter. So, substrate classifications. We've got our zeroary, our primary, our secondary, and our tertiary. And we'll refer to these as our airy halides because the only functional group we're really looking at is our halide functional groups, but it can really be anything with a leaving group. Okay? So wherever our leaving group is located, we will refer to that carbon as our zeroary, primary, secondary, or tertiary. Are there other classifications? Sure. What is that other classification? Talked about it already today. Allylic. Officially benzylic as well, but it's just a subclass of allylic. Okay, so if we have resonance contributing to this, that is also going to be a factor that we have to consider. We just don't have as nice a name for it. Okay? So our primary classifications are zero, primary, secondary, and tertiary. We've got examples for each of those up there as far as the alkyl halides go. Leaving group ability. Okay? If we take a look at this structure, what is the worst leaving group in that structure? What does the leaving group need to do? Take electrons. So when we're asked which is the worst leaving group, what we should do is look at what would happen if it was the leaving group. I'm going to do this right. Those are our 4 leaving groups. Which of those is god-awful? H minus. Why? I like that it's not going to happen. That doesn't help me. We could compare it as the base strength, which is ultimately a way of saying something about the stability of the negative charge. All of these are negatively charged, which makes one tick against all of them. But since we're forced to compare all of them, we then have to move on to the next thing. What's the next thing? Atom effects. Size. What atom is holding the charge in each of those cases? Hydrogen, oxygen, chlorine, bromine. What is our first difference between all of those? Size. Hydrogen is the smallest element on our periodic table, which means how stable is it going to be with a negative charge? Incredibly unstable. Which means it's the worst leaving group. It cannot stabilize that negative charge. Okay. We can then compare oxygen to chlorine to bromine. What's our comparison there? Oxygen is smaller than chlorine and bromine, which means second worst leaving group. Chlorine and bromine. Chlorine smaller than bromine, which means I wrote them in order. Bromide is our best leaving group. Chlorides are next, then OH, then hydride. Okay, so what we're doing is still using the exact same ranking system we've already been doing to evaluate our leaving groups, okay, as we did for ranking acids and base strengths. It's the same process. Okay. Some things that you can evaluate: polarizability, weakest base, electron withdrawing. All of those are ultimately the same thing that we've already done. We're ranking the stability of that negative charge. Okay. This is a figure coming from a different textbook that goes through and tries to do that base comparison. Ultimately, we've already done this. Charge. What is the stability of that negative atom? Anything that makes it more stable makes it a better leaving group because it needs to leave with those electrons. Make sense? Never mind. Solvent classifications. Your solvents kind of play a hidden role within your reactions. Yes, I did skip over nucleophiles and bases. Okay. They have a very minor kind of hidden role within it. They are almost always present, and they have a couple different roles that they play. The primary role is to get all of those chemicals into one place, into one phase. So if we ran a reaction with a solid and a liquid, the only place where the solid can interact with the liquid is on the surface of the solid. So everything on the inside doesn't react. But if I dissolve that solid and then mix it with my liquid, now all molecules have an equal chance of interacting. Okay, so our primary goal is to get everything to dissolve. So whatever we got to do to dissolve it, that's going to be one of our solvent choices. So we go back to solubility rules. So what would I expect to see between a solvent and the compound I'm trying to dissolve? Like forces. Hence the force diagram showing up again. Next aspect that we have to consider is kind of our secondary role. What does the solvent do to either stabilize or destabilize intermediates or structures within the reaction? Okay. For instance, if we look at the SN1 or the E1 mechanism, the very first thing that happens in those mechanisms is what? The leaving group leaves, producing an intermediate that is a positively charged carbocation. What should my solvent do? Should it make that carbocation less stable or more stable to speed that reaction? More stable. So I'm going to choose a solvent that can stabilize that positive as best as it can. What might I expect to find in that solvent? A negative charge. I want something relatively negative to stabilize it. Why do I have to be careful with that? I don't want the solvent acting as the nucleophile. Right? So we have to be a little bit careful with what our nucleophile versus our solvent is, and we have to watch that choice. But ultimately what we're trying to do is look at those two comparisons. I want similar forces between my solvent and my reagents, and I want to stabilize or destabilize potentially other things. Okay? Our classifications, you got polar and nonpolar as your broad category. Everything we've looked at in substitution and elimination has some kind of polar species within it, right? Which means a nonpolar solvent is a horrible choice because it will not dissolve our materials. It's not going to happen. Okay? So we need a different solvent. We'll use a polar solvent. But how can I further subcategorize polar solvents? I can look at protic and aprotic. A protic solvent tends to be more or less polar. More polar because it's hydrogen bonding, which is a stronger force most commonly because you're taking hydrogen with a very low electronegativity and you're bonding it to oxygen, nitrogen, or fluorine, all of which have the highest electronegativity. So we end up generating the largest dipole possible when we're looking at our protic solvents. Okay? So when we're trying to decide on a solvent for all of these mechanisms, we're looking at polar protic or polar aprotic. I'm pretty sure you guys are already pretty confident with assigning protic, aprotic, all that. Okay, because we did that a little while ago. Which type stabilizes a leaving group best? So what would your leaving group look like? Negatively charged. Which solvent would I like to help stabilize that negative charge? What do I need to stabilize that negative charge? A positive. Which solvent is going to give me the biggest positive for my buck? A protic solvent, because I'm getting the largest difference in electronegativity. So a protic solvent is going to be awesome for my leaving group. Well, in all of my mechanisms, what do I have? A leaving group, right? All of them have a leaving group. I need that. So why do we even bother to look beyond this answer? Because I would want a protic solvent to stabilize a leaving group. I need that. What's the next question? What's going to be the issue with a nucleophile? A nucleophile has a negative charge. If I use a protic solvent, what happens to the strength of the nucleophile? The strength of the nucleophile weakens. But in the SN1 and the E1 reactions, I don't care about the nucleophile, right? When we look at the rate, it's just dependent on the substrate, the leaving group leaving. So that means I don't need to care about solvents. What happens in the SN2 mechanism? What's your rate dependent on? The leaving, or our substrate and our nucleophile. If we weaken the strength of the nucleophile, what happens to the rate for an SN2 reaction? It slows down. Okay? So I want a different solvent when we're looking at the SN2 reaction Because if I use a protic solvent, I've now destroyed my nucleophile. Okay? How do we determine all of this? Negatives and positives, all the way through. Okay? Imagine just skipping through a forest. Just happens to be, I don't know, someplace scary. Nucleophiles. Okay? Nucleophiles are electron donors. So there's a couple trends that kind of pop up within this. One of the big things that we look for on our nucleophiles, very first thing, donatable electrons. Where are our donatable electrons? Lone pairs and pi bonds are our potential as nucleophiles. Okay? Let's push that a little bit further. After we found our donatable electrons, what's going to make a nucleophile even better? If that electron is now contributing to a negative charge. Why?
It's more reactive.
Why is it more reactive?
It wants to stabilize.
It wants to stabilize the negative charge by sharing the electrons, which is the definition of a nucleophile. So if we go through and look at a couple different nucleophile options, OH minus versus H2O, which is the stronger nucleophile? OH minus, because it's negatively charged, so that's our stronger nucleophile. HS minus versus H2S. HS minus. NH3 versus NH2 minus. NH3, no, I'm just kidding. NH2 minus is our stronger nucleophile. What happens with nucleophilicity when we shift across our periodic table, when we go left to right? Well, what's happening as we move from left to right on the periodic table? Left to right becomes what? Ignore nucleophilicity. Left to right becomes more electronegative. How is that going to affect nucleophilicity? Why?
It's more stable.
Electronegativity is the ability for the atom to hold electrons. What does a nucleophile need to do? It needs to give them up. Okay? So if we move to a more electronegative element, what's going to happen? It's going to hold those electrons in preference. Okay? So we would expect our electronegativity, okay, to affect our nucleophilicity. The more nucleophilic atom tends to be lower electronegativity, assuming all of those other rules hold true. That's why it's number 3, which means when I compare OH minus to F minus, which is the stronger nucleophile? OH minus. Okay. Why? Less electronegative than F minus. But what if I compare water to fluoride? Does that make sense to be looking at an electronegativity difference? No, because I should be looking at the charge effect first. Okay. The next rule, okay, which you'll notice is not in a big red box. Any ideas why it's not in a big red box? Much more difficult, and it's much rarer to see. More rare to see. You won't see it as often. Okay. Nucleophilicity has a dependence on size, and that dependence has a very strong solvent dependence. If you change the solvent, you change the nucleophilicity ranking, okay, which sucks. Okay. Taking a step further, not only is that an awful thing to be looking at or have to worry about, but it's not consistent. Okay. There are some atoms that will always be stronger nucleophiles. Sulfur will always be a stronger nucleophile than oxygen when charge is taken out of consideration. Why? Sulfur's an SOB. I don't know. Okay? That's just the way it works. The classic examples that we've got here for our rules and our solvent dependence go back to our halides. Okay? So if we're in a polar protic environment and we compare our halides, fluoride to iodide, bigger is more nucleophilic. So iodide in a polar protic solvent is more nucleophilic than fluoride. In an aprotic environment, okay, fluoride is the stronger nucleophile. We actually take advantage of that chemistry to do some other stuff later next semester. If we ignore solvent, bigger wins. All right, and this has to do with something known as the polarizability. The electrons are more accessible, which means we can have them act as a nucleophile. And we are well done